Hi, everyone. I'm Derek Dreyer, Program Chair, and it's my great pleasure to introduce our first keynote speaker, Azadeh Farzan. We're running a little late, so I'm going to keep this short and sweet. Azadeh received her PhD in computer science from UIUC. She did a postdoc at CMU, and then has been a professor at University of Toronto since 2008. Yeah, you can get set up here. Oh, I'll try talking to this. She has been a prominent, hopefully, concurrent interference. She's been a prominent member of our community for many years, serving as co-chair of CAV in 2016, program chair of POPL in 2021, and also as a member of the SIGPlan Executive Committee. She's done a lot of exciting work in the areas of concurrency, program analysis, and synthesis. And today she's going to tell us about a new perspective on commutativity and verification. Please join me in welcoming Azadeh Farzan.
Thank you. Can everyone hear me okay in the room? Fantastic. Thanks for the introduction, Derek, and for the invitation, the opportunity to share our work here today. So today I want to talk about commutativity and verification. So let me jump into commutativity right away. You see two atomic actions on, let's say, a global counter, an increment and a decrement. And we say these soundly commute, and by that we mean that if they appear in any program run, their respective order of execution is not going to change the outcome of the run. Right? So I'm keeping everything high level here. So here is an example of a run that they may appear in. We're ignoring everything else. And I can basically take two of these, commute them, make another kind of swap somewhere else, make another swap somewhere else. And the idea is that no matter how many of these I do, the run that I will end up with is equivalent to the original because every swap did not change the outcome of the run. This simple concept is basically kind of telling us that you have a commutativity relation that is sound in this sense. You have a definition of an equivalence on a set of runs that you can use. And this has basically appeared in many, many places, has had a lot of impact in programming languages research. So I'm going to mention a few for historical context before I get on with my business today. Probably one of the earliest ones has been due to a paper of Lipton in which he used commutativity to make big atomic blocks of code out of small parts and then argue that it's sound to do local reasoning in these big blocks. Now, this this idea has been consequently used in a lot of kind of proofs about, papers about proofs of programs, but also other surprising places like type and effect systems and many more. Another area that the ideas of commutativity reasoning has been very prevalent has been in model checking. In model checking, commutativity reasoning is used to basically curb the time and space of verification. The idea being that if you're looking for a counterexample to a property and you have already checked a run, you can forego the checking of all the commutativity equivalent runs. All of these ideas appear on the banner of partial order reduction methods and have been kind of appearing in thousands of papers, really. Last, for something a little different, it has been used in runtime monitoring and testing of concurrent programs. There, the flavor is a little different. The idea is that if you wanted to just randomly test a concurrent program, it's very unlikely that you see a bad behavior like a data race from a few random samples. So you want to try to extend your testing beyond the observed behavior, and commutativity reasoning is exactly the thing that is used to infer a lot of unobserved behaviors as behaviors of the program and test the whole bunch so that you kind of basically have a higher likelihood of hitting a problem like a data race. Now, the common denominator between the first two methods is this simple idea. If I have checked something or proved something, I can basically skip checking or proving all the other equivalent runs to it. And this concept has given rise to the concept of program reductions. So what is a reduction of a program? You see a simple concurrent program in which the increment and decrement that I showed you appear. If I kind of extend my sound commutativity beyond the counters to all the other actions of the program, which are also commuting because they're local actions, I can argue that that program is behaviorally equivalent to this program. Now, to be more precise, every behavior of the concurrent program, for every behavior of the concurrent program, I have a behavior in the sequential program that is commutativity equivalent to it. And this is exactly what a reduction means in the context of this talk, and as it was introduced by Lipton originally. So that one, of course, is not the only one. You would immediately observe that I can swap the order of, I'm stuck. You can swap the order of, I think the presentation on the other side is stuck. My slides are going ahead. So what is it that we should do? Unplug and plug again. You didn't even feel my unplug. Should I do it one more time or wait for it to come up? Okay. Let's see. So that one is not the only one. And if we kind of look at it quickly, we see that, okay, it's okay to reverse the order of the threads. That is also a reduction. But I can play more games with this. I can basically argue that if I execute the two threads in lockstep, for the same reasons, I will get another reduction of the program. And then I can take this idea even further and execute the threads in different paces at lockstep. And you will quickly see that this simple program basically has an infinite space of possibilities of program reductions, which are all sound to verify in place of the original program. Now, let's look at this space and see what sort of opportunity it presents for verification. So the first two sequential programs, we can immediately observe they have quadratically fewer control locations. So if we give them a proof, this proof is going to have quadratically fewer assertions, quadratically fewer verification conditions to check. So we can say that these have a simpler proof in some sense of the word, which is precise, which means I have to spend less time and space in the verification of that proof. But then if I kind of inspect them a little more carefully, I will see that they all share a problem in some sense. All three programs require an annotation like the one that you see on the screen. I need to basically capture the effect of the loop, which has to be captured using a nonlinear assertion. And solvers don't like nonlinearity, which means that if I were in a fully automated setting and I wanted to try to get a solver to give me those annotations and or verify their verification conditions, I would get stuck, even though the programs are super simple and super trivial. On the other hand, if I look at the lockstep reduction, I would immediately see that, yes, same as before, quadratically fewer control locations, so a simpler proof in that sense. But at the same time, this program can be proved correct using a very simple loop invariant. So this one actually can be proven using fully automated techniques. And the proof is in some sense simpler in a qualitative sense beyond the quantity issues. So this kind of simple observation with this super simple program is really the foundation of the view of the talk that I want to give to you today. That this presents an opportunity. I can really think about any sort of algorithmic verification scheme as something that tries to actively search for a proof. And while it's trying to search for a proof, it talks to a logical reasoning engine. But logical reasoning engines come with limitations. So the program and the property of choice might force the algorithm to hit an undecidability or a high complexity barrier that is kind of intrinsic to the logical reasoning engine. And if that happens, the algorithm is stuck. There's really nothing that it can do to unstuck itself. But in some cases, like the example that I showed you, there is an opportunity. We can try to say that we're not going to give up. We are going to give up on verifying the program, but we are going to basically search for an alternative program that we can actually prove correct instead. So it's kind of like a paradigm shift in which you view the algorithmic verification scheme as not just a proof search, but a search for a proof and a program concurrently. A program and a proof for it that can be basically replacing the original verification goal soundly. Now, why am I insisting on an automated search for a program? Because most of these reductions are actually quite ugly. When I showed you this one, waved my hands and said, this is a lockstep reduction, it's sound to verify in the place of the original program, I was effectively lying to you. It's not this, it's this that is the sound lockstep reduction of the program. I need to account for all the behaviors in which one loop may overtake the other one in the count of the number of executions, except later on when I have access to logical reasoning, I would prove all of those infeasible. But commutativity reasoning cannot let me prune those parts out. So this is the program, this is the reduction that we will end up verifying. But we still can verify it the way that I mentioned it. So my view is you should not force people to look at this ugliness. You should let algorithms do that. And the idea, once we can actually pull it off, has broad applicability. I'm hoping the tiny example has already convinced you that in concurrent and distributed programs, because there is a lot of redundant behavior due to the interleaving nature of things, you have opportunity to actually kind of look for these alternatives. But also another maybe surprising thing to the audience is the area of relational verification and a specific sub-area of it, hyper-property verification, which is coincidentally where we actually started from in this work. There, because self-composition is used as a proof method, you kind of have exactly the same theme. And for people who know this area, you can kind of think of a program alignment that is used to prove in a self-composition framework as an equivalent of a reduction. So anything we invent that would be useful for the things up there will be useful for the things down here. So same methodology, same solution. Now, I'm hoping that this tiny introduction convinced you that this is a worthwhile goal. So let's try to switch kind of perspective to see, okay, can we actually pull this off? Can we make the new paradigm happen? To do this properly in this talk, I need to lay a foundation. I need to pick an algorithmic verification setup and basically present the ideas to you there. But I want to say something a little bit more, that this choice of mine is not arbitrary. I'm actively choosing what we call operational proofs. And because I fundamentally believe that this is the framework that makes it easier compared to all the others to make this happen. Now, operational proofs are proofs of programs that take an operational view of the program. So we say that the program is correct if we have proved all of its behaviors correct. Or you can kind of think about the simple proof rule in which we say that there is a concept of a proof, which is a set of behaviors that we construct as we go, and we know they're correct. And the correctness of program is basically through the subsumption of the program behaviors by the correct by construction proof behaviors. Now, of course, for this to actually algorithmically happen, I need a few ingredients. I need to be able to represent the proof, represent the program, and have a decidable subsumption check. Only then I can say this proof rule is algorithmically realizable. Now, we have done a lot of research on this kind of framework, which is beyond the topic of this talk. You can check it out if you want. For the purpose of today, I can just very quickly give you a high-level idea. So the algorithm works like this. You start with an empty proof. You kind of ask, does this subsume the program behaviors? Of course not. You get a counterexample whenever the answer is no. Now, you have to check whether this is a real counterexample or not. If it's a real counterexample, you have found a violation, a witness to the violation of the property, you're done. If not, you can actually use your logical reasoning engine now to prove the counterexample correct. And now that you have a proof of counterexample, some magic happens in this box that I'm waving my hands and not explaining, in which you kind of update your proof based on the proof of this behavior. The idea being that kind of your proof now includes the proof of this behavior and all the other behaviors that admit a similar proof. And then I can go back and ask, does it subsume the program now? Whenever the answer is yes, I'm done. Whenever the answer is no, I will go around this loop and basically grow that proof object until I'm done. Now, why am I insisting on liking this framework better than some others? The reason is that the proof, in some sense, grows separately from the program. In a classic setup, I know what program I'm proving from the beginning, so I have options. In this setup, I don't know what program I'm proving. I'm looking for a program to prove, which means I don't have access to the program. And a kind of classic, like axiomatic method that needs to do induction on the structure of this program, which is unknown to me while I'm going around this loop, I at least don't know how to start there, right? But here, I can sort of keep the two separate, make progress, and hope that eventually the two sides will meet and converge. So this is really the reason I like this framework. Now, how do we incorporate commutativity into such a framework? If you understood the idea, a very trivial thing would immediately occur to you. So you say that, okay, you had this proof rule, you're using this framework, why don't you change your subsumption test to a test in which you would every time take your proof object and blow it up to commutativity. Now, whatever you have proved, you have all these other behaviors that are also correct up to commutativity, and you have effectively taken advantage of commutativity reasoning. And it would have been fantastic if I actually could do this. The problem is I can't. Even in the simplest cases, the simplest models for the program and the proof, which are regular languages, this subsumption test becomes undecidable, which means the proof rule is valid, but I cannot have an algorithmic realization of this proof rule. So what is the way out? The way out is exactly the idea of reductions that I showed you as examples basically when we started this talk. So we can say that we can rely on this classic result, which is a theorem that says there are certain classes of reductions of the program that are nicely representable, and therefore we can check the subsumption of their behavior into the proof. So what are these class of reductions? They're called lexicographic reductions, in which you use a simple ordering on the program statements. That simple ordering on the program statements induces an ordering on the program runs. Now you have an ordering on the program runs, and what you do is you say that my representative picker from every equivalence class of the program is going to pick the least element. And this is, canonical, we understand it, but the beauty of the theorem is that it says that now that object that picks these representatives is nicely representable, it's regular. And as such, you can actually test the subsumption like you would before with any normal program, okay? Now, as an example, if I take the concurrent program that I showed you at the beginning, and I say that all the left thread statements are before in order than the right thread statements, and you compute such a reduction, you will get exactly the sequential program, that the first thread starts and then the second thread finishes. If I swap the order, I will get the other concurrent program, and I can play with this order to get all these other programs. So the nice thing about this family of reductions is they kind of select a unique representative from each class, so they're sound and optimal. And more importantly, they're parametric. You can play with the order and get different reductions as a result. So now we can go back to our original proof rule and replace the program with a reduction of it. Now, this reduction would be constructible. That subsumption check would be decidable. So this proof rule can replace my original proof rule. Now, of course, it shouldn't be kind of lost on anyone in the audience that I have not yet delivered on the promise of searching for a reduction. This is just one reduction. But interestingly, just having access to this, let's say, weaker than the ultimate goal proof rule already has a lot of impact. So if you kind of have a portfolio tool in which you pre-select a handful of reduction in advance, so independent of the instances, and over 1,200 standard benchmarks from verification conditions, you compare handful of reductions with no reductions at all, you do significantly better. You can basically solve 50 more benchmarks, and the entire kind of suite of benchmarks can be solved in half of the time. So a lot of power even in this kind of halfway there step. But let's get back to what we wanted to achieve originally. We have an undecidable but ideal rule on the left. We have a decidable but non-ideal one on the right. So we want a middle ground. And the observation is that the one on the left effectively is saying there is a reduction in the universe of all possible reductions, which are typically infinite because we have undecidability. And I'm looking for that golem one, but I cannot because this is undecidable. So how about the middle ground be that we pre-select a set of reductions, which is not everything, but it's an expressive set, and deliver between the two. And hopefully, whenever the original set is infinite, this set of reductions is going to actually be infinite as well. So we basically hit infinitely many reductions inside the possibility of infinitely many reductions originally. And in this set, we are saying we want to check whether one of these reductions is actually subsumed by the proof. So let's go back to our operational loop. And so the subsumption check is going to be replaced by this. But naturally, to make all of this happen, I need to answer a few questions. I need an algorithmic check for this. I have to show that this is actually decidable. But that's not all. Once that subsumption check fails, I need a counterexample. And the question here would be, this counterexample is witnessing the delta between the proof and which one of these infinitely many reductions. And then the relevant question is, okay, that counterexample, when I go back and construct a proof for and advance my proof, is advancing the proof against which one of these infinitely many reductions? If I pick and choose here, I am not doing any better than the kind of halfway rule that was just choosing a reduction anyway, right? So if I answer all of these questions successfully, I have made this whole thing work. And the key is to kind of the selection of a suitable set of reductions that will make all of this come together. So what is this set of reductions? We basically borrow the idea of the classic theorem that I showed you and sort of expand it. The classic theorem was using a flat order on the program statements. We say, how about we actually take what I call contextual orders on program statements. So now you let the program statements to be ordered differently depending the context in the execution that they appear in. So you have, at the end of a different history, a different ordering of the program statements. So now, as opposed to having, finitely many flat orderings on the program statements, I have infinitely many contextual orders that I can use in my program. Then we can kind of make this observation that a contextual order like this, in the same exact way that a flat order would induce a lexicographic order on the program runs, which means that now, again, I have a selector to pick a representative from an equivalence class of executions from the program, which means that that selector is going to give me a program reduction. So like before. The difference now is because I have infinitely many, the difference is now because I have infinitely many contextual orders, I will have infinitely many lexicographic orders. And other than some pathological cases, they will give me, in the typical cases with normal programs, infinitely many choices of program reductions. Okay? So this was just the definition of a set of reductions that are suitable. Now let's switch our view to the representation of them. But to make sure that everyone is with me, I will show you a quick example for all of this to kind of set it. So here is a tiny program, just graphically. 2 threads executing blue and purple in parallel, some arbitrary numbers. Let's say for whatever reason, I'm interested in this magic reduction, 2 blues against the purple. Can lexicographic reductions give me this exact reduction? The answer is yes. I can pick a contextual order like this. I can say that at the beginning, I will prefer blue over purple. Whenever the last thing that was executed was purple, I will prefer blue over purple. Whenever the last 2 things that were executed were purple and blue, I will still prefer blue over purple. And only when the last 2 things were blue, I will switch my preference and prefer purple over blue. And you can already see the theme. This is not unlike kind of a priority scheduler, right? But contextual. And this is going to basically, from that program, with the assumption of commutativity of blue and purple, give me exactly the reduction that you see. Now, of course, if you have been paying attention to me, you should say, wait a minute, that reduction doesn't look okay, and you would be right. The actual ugly reduction looks like that. But the example that I showed you is not going to be any different. All the junk on the side are the cases that you have no option in executing things, so whatever ordering you are imposing is not going to matter. You have only one thing to execute, and you will execute that thing. Okay? Now, the class of lexicographic reductions are, neat, but the true purpose of them is that we can actually represent them effectively. There is a finite representation for the infinitely many lexicographic reduction. And this is achieved through three automata. So there is a simplest class of three automata, we call them looping three automata, that can represent precisely all the lexicographic reductions of the program up to all contextual orders. And you can kind of think about it as every tree that is recognized by this automaton would correspond to one reduction. So the moment we have representation of the reductions as a tree automata, we can rely back on classic automata theory in some sense. Actually, this is a little non-classic. It's a theorem that wasn't in the literature, but we proved, but similar. And we can show that it's decidable now to check whether one of these reductions, one of these trees, is subsumed by a proof which is a regular language. And more importantly, this can be done in linear time. This problem basically reduces to, the Horn satisfiability problem. And as such, you can do it in linear time. So now we have answered the question, do we have a decision procedure for this? What about the other two questions? So whenever the subsumption passes, we are good. When it fails, what then? And the beauty of the looping tree automata and this class of reductions is without you putting any more effort, you will get this other theorem for free that says that whenever the subsumption test fails, there are finitely many counterexamples that witness the difference between the proof and the reductions. So you can basically take these finitely many counterexamples, you can test them, you can give them proofs, you can update your proof based on them, and you know that you have made a non-zero progress across the board, across all the many infinitely reductions. Which means that the new algorithm, the new operational loop, basically has exactly the same progress property that the classical one had when we were just trying to prove one program and coming up with a proof for that one single program. All right, so this sort of ends the first part of my talk, in which hopefully I have convinced you that we can deliver on the promise of combining the two searches together algorithmically. Search for a reduction and for a proof of a reduction, all in one unified kind of framework. Just so that I show you that this does make a difference. If I compare the other tool that I showed you earlier, that hand selects a few reductions with a tool that actually searches for reductions over a category of really challenging benchmarks. These are the ones that you cannot prove without reductions. The one that searches for reductions does almost twice as better. Okay? So it's worthwhile to actually go through this trouble. Now, I have answered this question. We can automate this. I want to briefly, in the second part of the talk, turn my attention back to the first question, but a refinement of it in some sense. So this seems like a lot of effort. Is there really out there enough commutativity to exploit to make this effort worthwhile? And I can answer this question starting by using a few examples to motivate a few ideas. So first, let's turn our attention to the context of message passing concurrent programs or distributed programs. I think it's clear to everyone in the audience that when you have a send and a receive on a same channel in such programs, the send would actually commute to the left of the receive, but the receive would not commute to the left of the send because the receive could be blocking. We don't have the order of execution doesn't change the outcome anymore. This motivates the idea of an asymmetric commutativity relation, which we call semi-commutativity. So if, I should be able to deal with this as well, otherwise I can't do anything here. But if I'm super keen to commute the receive to the left of the send, I can do that. I can say that, okay, not everywhere I can do this, but in the context in which, in the history of the execution, I have more sends than the receive would actually commute to the left of the send. And this motivates the idea of contextual commutativity, which is commutativity that doesn't globally hold, but holds in certain contexts, and we want to still be able to exploit it in those contexts in which it holds. And finally, even a simpler kind of example, if I have two updates to a global variable, they don't commute under any of the notions that I showed you before. No context, no semi, nothing. But I can kind of ask myself, does it really matter that x is 5 or 7 at the end of the disk? What if for the particular property that I'm trying to prove about the program, it suffices that I show that x is positive at the end of this? Then I can change my view of those statements to this, and now these two statements would just commute, without any problem. And this motivates the concept of abstract commutativity, taking, dropping the precise meaning of the statement and taking an abstract view of them. So if one is serious about exploiting commutativity out there, one cannot really leave these three options on the table. One should have a way of trying to exploit this. And I want to just very briefly tell you a little bit about what we know about either of these options. Okay? So semi-commutativity is rather easy. I'm not going to really get into it, other than telling you that more or less it can be done the same way that you can deal with a symmetric commutativity relation. The only thing that you will lose in this game is that you have to give up the optimality of your reductions. Now your reductions may have a little bit of junk in them. And this, for the people who know and understand them, effectively gives you the same kind of power of reasoning like Lipton left and right movers that are kind of semi-commutativity type of arguments. Contextual commutativity is far more interesting. In contextual commutativity, I want to be able to say A and B commute in one context, but not in the other context. And the key to make this happen in the framework that I've already presented to you is to choose the right view of a context. And the right view of a context is to take the history as a context. I'm kind of contrasting this against, for example, taking the state as a context. Okay? So I would say that at the end of one history, certain histories things commute. At the end of certain other histories, things don't commute. And then you can see that the commutativity relation can be viewed as a function like this, from histories to a choice of commutativity. And I'm showing you this because it looks super like the contextual orders that I showed you before. And I want to hopefully here wave my hands and tell you exactly the same way that the three automata can enumerate different contextual orders to give me different reductions, they can enumerate different contextual commutativity relations as well. So now I'm enumerating both contextual orders and contextual commutativity relations, and every time a reduction would be based on the particular choice of the commutativity relation and the order at that point. But naturally, this is just enumeration. Not all these contextual commutativity relations are sound. In fact, most of them aren't, because I'm just saying everything goes, right? So what is the solution to this problem? Enumeration easy, enumeration of sound ones super difficult. Now here is where the operational proof rule shines, in my opinion, one more time. Because I'm kind of keeping my proof and my program separate, this object that is enumerating all these programs can just basically enumerate everything. But I can piggyback on the subsumption check to the proof to actually certify the commutativity relation that has been used for the particular choice as well. So now subsumption becomes, are the behaviors of this reduction included in the proof? Yes. Is the commutativity relation you used to construct this reduction sound in the sense that the proof can actually certify it as sound? And if the answer to both questions is yes, we will basically certify that reduction. And if no, we actually get a bonus out of this. we get counterexamples that are no longer just counterexamples to correctness. They can be counterexamples to not having enough ingredients in the proof for commutativity, which means in our proof effort, we can actually kind of try to add reasoning that just goes there to give us more commutativity. So hopefully we can have enough commutativity to be able to prove one of the reductions correct. All right, just to kind of, again, show you that this does matter, if you don't do any semi or contextual commutativity, as opposed to if you do, it makes a huge difference. Like 3 times more the number of benchmarks can actually be proven. Naturally, the benchmarks were selected to be sophisticated, like message passing programs, array programs, in things in which context and semi-commutativity mattered. But in this class of programs, you really need this to be able to get through. All right, finally, abstract commutativity. This one, in some sense, is the biggest white whale of them all. So it's simple enough to define abstract commutativity. You just use the abstract semantics instead of the concrete semantics to say, when is it sound to say 2 things commute? But naturally, the trick is, where should this abstraction come from? And is the abstraction that I have picked okay to use in reality? Right? The tension between abstracting too much or too little. So first, in the particular operational framework, we have to kind of understand what soundness means. So we have always in this framework a partial proof object that we are working with. And soundness really means that if I take the closure of this proof object up to the particular commutativity relation, the abstract one, everything in that closure should be correct. This is what soundness means, because this is really fundamentally the idea that I'm using here. Now, fortunately, whenever I have an abstraction candidate and I want to test whether this is true or not, I can easily test it. This is basically kind of thinking, hand-wavy. The proof has ingredients. It's based on a bunch of Hort triples, and I have to just make sure that my abstraction preserves the validity of those Hort triples. The moment that check, which is standard, passes, I know I have this sort of soundness property. So I can always be sure that whenever I have an abstraction, I can check that things are sound, so the loop is operating correctly. But operating correctly is kind of like the minimum requirement. The question is, where should that abstraction come from that would give me the desired commutativity relation, right? So let me take a tiny one-slide detour and tell you that if you don't know where it comes from, but you pick a generic one, you still are ahead. So a very, very coarse abstraction. You look at your proof, you see what variables have not even been mentioned in the proof, which means they're maybe irrelevant to the argument. And you existentially abstract away those variables from the semantics of all your statements. With this abstraction, if we compare abstract and concrete commutativity in a lot of benchmarks, in their standard properties that they came with, abstract commutativity will do a little worse than concrete commutativity. But if you switch to a lightweight property, for example, if you're checking memory safety, then abstract commutativity takes over and does significantly better, proves a lot more benchmarks in a fraction of the time. So even if I'm not tailoring my abstraction to my instances, for generic instances, this gives me power. That has to be kind of explored. But going back to the question that I asked, if I have a particular instance, a program and a property, and I'm really searching for a custom tailored abstraction that would get me through that particular kind of obstacle, can I really search for it? And the answer is no, right? And the reason is that the intuition that, well, at least we had, and I think maybe people in the audience would share it, that abstractions and commutativity relations have this nice monotonicity property with respect to each other, right? The more you abstract, the more commutativity you are going to get. Nonsense. It doesn't hold. Here is a kind of tiny example with the same abstraction that I mentioned to you before. These two array accesses in the concrete commute because you know they're to 2 different cells. But if you abstract away, for whatever reason, variable I, now they become these two statements, right? You're accessing somewhere, you're updating somewhere in the array. Because you have lost the index information, you cannot separate these two things from each other anymore. And in the abstract, you no longer commute. Okay? So this kind of tells you that by take a pair of statements, move up and down the abstraction ladder, I can gain and lose commutativity as I go, really. But even worse than this is, if you take the whole view of the entire commutativity relation, you can gain commutativity somewhere and you can lose it somewhere else, which means the commutativity relations you get at different abstraction levels are all over the place. They're incomparable in the general together. So if I wanted to try to search for an abstraction, I'm turning an abstraction knob that is basically not connected to anywhere that I care about. And this makes it really difficult to search for an abstraction that would give me a commutativity relation. But like any good researcher, when faced with a problem you cannot solve, switch to one that you actually can solve and hopefully sort of solves the same problem. And this is, okay, for whatever reason, I have been all over the place, collected a bunch of abstractions, they give me different incomparable commutativity, and I want to use them all. I know I cannot pick a best. Can I use them all in one verification goal? And the answer is yes, under circumstances. So this is what we call a stratified commutativity. So we want to kind of basically use these commutativity relations. I'll show you a tiny schematic with two, one concrete and one abstract, but the idea would generalize to any number. Okay? So let's say I have a proof, and I have a concrete commutativity relation. I know everything in the closure of the proof up to that commutativity relation is safe. Then I'll take an abstraction, and I know that this abstraction is safe because I have checked it against my proof. So I know the safety of everything in the closure up to the abstract. Now the combination of the two, because the abstraction is strictly more abstract than the concrete commutativity, is that it's safe to basically take the closures in a strata, right? First up to the concrete, second up to the abstract. And the order really matters, the order of abstractions and the order of taking the closure. So if you did it this way, you would get unsoundness. Why? Because the inside closure is safe, but you have not actually checked, and you have no means of checking that the abstraction is safe with respect to the proof object, which is the closure of the original proof. The entire point of using commutativity was I was too lazy or too stupid to give a proof to that closure, right? So I don't have ingredients for the proof to check against the abstraction. I have no way of saying whether this is safe. But the one in green, safe. So we can actually use this one. So if you kind of think about the beginning of my talk, I told you we really cannot check closures, so we check reductions instead. And I'm here to tell you that, again, because we cannot, of course, check double closures, we can turn that into a double reduction. And here, if you don't follow me, don't worry. I'm just trying to finish the thought, but it's okay if you don't follow me. That is really unknown whether it's decidable or not. But it doesn't matter because we can do something better, something even better than that double reduction, which is decidable. The only thing that we have to do is we have to throw in the middle the runs that we have already proven correct into the mix. So if we do that, we get a decidable double reduction proof rule, and it basically always works as long as you maintain the order of abstraction, the most abstract outside, the most concrete inside. So this is the way, the condition under which we can combine any number of commutativity relations all in one verification goal. All right. Just kind of to mention this, there are other ways of combining commutativity relations. For example, the tool Civil that is using ideas of commutativity to verify concurrent programs actually uses a different scheme in which it combines two commutativity relations that are incomparable with respect to their abstraction. But that one also, in some sense of the word, is boutique. So I'm kind of very interested in the general question of beyond, a concrete order on the abstractions. Are there other ways in which it's sound to combine commutativity relations? It would be interesting to discover more so that we can actually do more with this, short of solving the original problem that I put behind me. All right, so let's kind of try to wrap up. And with this, I want to turn my attention from the past to the future. If you have been kind of paying attention, even though I have not been saying it very explicitly, everything that I showed you is about safety. And the class of programs that would fit all the kind of theory that I mentioned would be the class of programs in which you have a fixed number of threads, or in the case of relational verification, fixed number of components in the self-composition. Naturally, the obvious kind of thing is how can we go beyond, more expressive properties, more expressive program classes. So I'll just kind of briefly tell you that we have looked at a few of these, but there are a lot more that are pending that one can look at. So we have looked at termination of concurrent programs, how to use this basically for liveness proofs. We have looked at unboundedly many threads case so that we kind of break the fixed thread barrier, and we are kind of currently looking at recursion, in which we cannot deal with concurrency because that would be undecidable, but we can try to maybe deal with the hypersafety verification in the context of recursive programs. But a lot of other things like hyperliveness, other program models, basically a lot more research to be done, just expanding expressivity here. But what I want to focus on a little bit more as kind of future work concretely are two things that I kind of view as more grand challenges. The first of them is the fact that anywhere you look in commutativity reasoning, not just this area, all the three things that I opened as historical context, everywhere that I have personally seen, commutativity is always about commutativity of the atomic steps of the program. But you can easily see that, here I don't have a commutativity of a decrement and an assume maybe, especially if the decrement is blocking. But if I kind of look a little further back and I see that I have an increment and a decrement together, which effectively form a skip, that skip would always commute against anything, including this assume. And I don't have to look at context, I don't have to abstract, I don't have to do anything fancy. But this business in which you take commutativity beyond atoms to kind of sequences or blocks of code is effectively unexplored entirely. So ideally, what you want to do is you want to let parts move, and you want to let parts form alliances and move together, and different alliances at different times. This is kind of like the true power that has been left completely untapped in this framework. Of course, there is theoretical evidence a little bit that the moment you want to do this, things become difficult. A lot of classic noise results that all of this rely on immediately get falsified. But we started with Umang to look at this a little bit, and we managed to kind of put our foot kind of through the door, so to speak. We have kind of been able to show that in the simpler context of runtime monitoring and predictive testing, you can actually make this happen a little bit. But I want to emphasize that and you can come see my talk this afternoon if you want to learn more about this. But it's really important to say that work is scratching the surface in one of these categories that I showed you. All the other categories, nothing completely unexplored. It would be wonderful if we see more research in this particular aspect in the future. And lastly, this community has been great at taking classic verification, which is viewed as proof search, and basically creating this kind of cases in which a human and a machine can basically together have a really, really nice alliance and make big verification goals happen. So it would be wonderful if we could answer this, and I have absolutely really no idea, in how we can try to incorporate humans and human insight effectively into this other paradigm that I showed you, which would combine a proof search and a program search. And moreover, the proof search part, as I again showed you a little bit, is not the program search part is not really just the program search, but implicitly a search for an ideal commutativity relation that would give us the ideal programs as well. So this picture and where human insight can effectively participate in this would be the thing that would actually kind of make it happen for really, nice big projects beyond smaller things that fully automated verification can take care of. And I'm hoping that the community will rise to the occasion and kind of help with this, because I don't have that much experience kind of trying to sort out this sort of problems. And with that, thank you for being here and listening to my talk, and I can take questions.
We have time for, thank you, Azadeh, for a great talk. We have time for several questions. So come to the mics. There's a mic over here, or are the student volunteers around? Yeah, if you could pass around the mic.
Hi, that was a very nice talk.
Thank you.
I wanted to ask you, have you looked into, using properties of a language to get more commutativity relations? For instance, in Rust, you know that different variables refer to different, mutable variables refer to different disjoint regions of memory, so you get sort of more commutativity than you might in something like C.
That's an excellent question. The answer is no. But mainly because, in all of this work, we work with a very simple programming language, right? But fundamentally, I can acknowledge, related to your question, that checking commutativity for simple statements, easy. As program statements become more and more sophisticated, this starts to become, way on the thing, especially with abstractions, because abstractions make the semantics of statements very sophisticated. And then you can basically get stuck checking commutativity of a super sophisticated thing. So I absolutely am with you that any such thing that would basically lift the burden from those tests would be a huge impact in making these ideas work much better.
That was a great talk, thank you. One thing that you didn't touch on is how successful these are in practice. So are these sorts of techniques used in industry every day? Are we a decade away from being able to do that usefully? What's the current status of actually using these things?
So, the entire research is not more than, mine is not more than 5 years old. Like the beginning point was 5 years ago. So naturally not being used in industry every day today. Some of the ideas, for example, the part in which you don't want to enumerate every reduction, but a handful of them, I don't see any delta between what was automated verification before and that. So for that, I don't see any kind of problem of deployment like immediately today. We are not making anything slower or worse. We are just making things faster. The part of actually enumerating a lot of reductions does make things slower, right? You're doing double search instead of a single one. You have to pay a cost for this. So for that, my view is that if that is supposed to happen in practice, we really need to now step out of the theory into this practice of one of the two things. Either kind of pare back, just not search everything, search like a subset that is still good but can be done more effectively, or what I actually mentioned at the end, that you would sort of get a little bit of insight in a form that is not clear to me today from the user. So the user would say, here is an idea of a reduction. Why don't you just go and prove it sound? And then effectively, I would give a big leg up to this search in which I go back exactly to the status quo. So basically the future work that I mentioned is all in the direction of trying to bridge that gap and make it happen. But so depending on how that works out, maybe 5 years.
Thanks a lot. That was a really great talk. I remember, so totally on an unrelated field, but you may see like how it relates. I've seen like on binary and assembly level verification, some work that were also quite close. So if I understand well, the commutativity relates quite closely to observational equivalence with respect to the assertions you want to prove. And I've seen a lot of work on assembly with like more syntactic, like use-defined chains or diffuse chains that were also trying to slice the programs with respect to some of the assertions to try to create a kind of normalized form with commutativity, so you can extract chains and you can prove specifically on each of the chains separately. Is there something like a kind of normalized form of what you would like to commute that would be more efficient by saying, like, for instance, you take all the send before, you take, like, can you do this kind of thing also?
If I understand you correctly, because I'm not like intimately familiar with this research that you're mentioning, the lexicographic reductions that I mentioned to you, you can really view them as normal forms, right? The only difference is that they're parametric normal forms. You change your order, you will get a different normal form. And I kind of, to keep this talk high level and pleasant for everybody, I kind of jump over a lot of details. So for example, even if I'm constructing one reduction, I can just construct one, but it will be ugly and huge and completely useless for verification. So a lot of research has gone into how to take a make a compact representation of that thing that would actually kind of have the results that I showed you, that it would work faster, like half the time, right? So there is definitely some connection there. It's just that I don't know the normal forms that you're talking about were constructed with what goal in mind. I can say that these ones were constructed with the goal of the most compact kind of representation I can get. But I don't know whether being small matters there or not. But fundamentally, normal forms are the thing. There is no other way of doing this, right?
Great, thanks.
I'm going to take the last question from Discord. I think that the questioner says, I think there are connections between tree automata and E-graphs or quality saturation. What are your thoughts about connections between E-graphs and your techniques?
I mean, I understand exactly at that level that to me, coming from automata theory, E-graphs are tree automata. So beyond knowing that E-graphs and tree automata are more or less the same representation under two different guises, I don't know what connection there is, but I can maybe answer the question slightly more intelligently by saying that and I think I've seen a little bit research in this team that tree automata, we use tree automata to effectively represent a set of programs that have a particular purpose here. We have actually started looking into this, but with the whole LLM explosion effectively given it up entirely, that you can use E-graphs for the purpose of synthesis, which E-graphs are used. You can use tree automata for the purpose of synthesis in a sense that you can try to enumerate a lot of candidate synthesis programs and then pick the correct one more or less using the mechanism that I showed you for proof checking. So there are definitely those sort of formal connections, but the devil in this case is whether it's going to be effective. And for me personally, the moment enumeration kind of went through machine learning and LLMs, enumerating programs with tree automata for the purpose of synthesis seems like, hold that thought and see what happens before kind of investing too much time in this.
All right, let's all thank Azadeh for a great talk.